Welcome to Deep Thinkers. Tonight, there is nowhere you need to go, and nothing you need to solve. There is only a slow story about the ground beneath you and how it is not as still as it seems. So let your shoulders drop. Let the weight of the day slide off the edge of the bed and pool somewhere on the floor where you can leave it until morning. You do not need to follow every word. You only need to let the words carry you, the way a slow river carries a leaf, without effort, without hurry, down and down, into the deep dark of time. Here is the first strange thing. Right now, as you lie there, the ground you are lying on is moving. Not shaking, not lurching, nothing you would ever feel. It is drifting. The great plate of rock that your house and your city and your whole familiar landscape are riding on is sliding across the face of the planet, slowly, patiently, at about the speed your fingernails grow. 2 centimeters a year, maybe 3, maybe 4. Slower than the minute hand of a clock by a factor almost too large to picture. And yet, it never stops. It has not stopped for a single day in all the long history of the world, and it will not stop tonight while you sleep. Out in the middle of the Atlantic Ocean, far from any coast, there is a long seam in the seafloor that runs from near the top of the world to near the bottom, like a scar stitched down the center of the sea. It is called the Mid-Atlantic Ridge. And along that seam the ocean floor is very quietly pulling apart. New rock wells up from below, cools, hardens, and is carried away to either side, a little each year, so that the Americas on one side and Europe and Africa on the other are drifting ever so slightly further apart, with every year that passes. A few centimeters, the width of a couple of fingers. That is how fast the Atlantic Ocean is growing. It is widening while you breathe. And on the far side of the world, something opposite is happening. The Pacific Ocean, the biggest ocean on Earth, the vast blue expanse that swallows almost half the planet, is quietly shrinking. Around its edges, the seafloor is not being made. It is being swallowed. It slides down beneath the surrounding continents and sinks back into the hot interior of the earth, disappearing a little at a time, so that the greatest ocean the world has ever known is, very slowly, being closed. One ocean opening, another ocean closing, the whole surface of the planet caught in a slow tide, breathing in and breathing out over spans of time so long that a human life is less than the blink of an eye against them. This has happened before. That is the part that is difficult to hold in the mind. The great ocean of the deep past had a name. Geologists call it Panthalassa, the world ocean, the single enormous sea that once wrapped almost all the way around the planet. And Panthalassa is gone. Its floor has been almost entirely swallowed back into the earth, sheet by sheet, over hundreds of millions of years, until scarcely a trace of it remains at the surface. An entire ocean, wider than any ocean we know, simply vanished into the depths. If a whole ocean can disappear, then nothing on the surface of this world is truly permanent. Not the seas, not the shapes of the continents, not the map you learned as a child. Which raises a quiet question, one that scientists genuinely cannot answer, and it is the question this whole slow journey circles around. If the Atlantic is opening and the Pacific is closing, if the continents are always drifting, always rearranging themselves like slow clouds, then where are they all going? What will the map of the world look like, not next year, not in 1,000 years, but 250 million years from now? And the honest answer, the answer the best minds in the science will give you, if you ask them plainly, is this: nobody knows exactly. Nobody can point to a single future map and say, this is certain. Nobody agrees on which of several possible worlds the continents are drifting toward. But they do know something remarkable. They know that the continents will not stay scattered the way they are tonight. They know that sooner or later, on the slow beat of a rhythm older than any living thing, all the land is going to come back together again. Every continent, every island, all of it, gathering into a single, enormous mass, one landmass surrounded by one ocean, the way it has gathered before, more than once, in the deep past. A supercontinent, the next supercontinent. And there are, in the minds of the people who study these things, four main pictures of what that gathered world might be. They have given each of these possible futures a name, and the names alone are worth carrying into sleep. The first is called Pangaea Ultima, sometimes called Pangaea Proxima, a world in which the Atlantic Ocean stops widening, reverses, and closes back up, folding the continents together again around Africa. The second is called Nova Pangaea, a world in which it is the Pacific that finally shuts, and the continents drift across into that closing gap on the far side. The third is called Orica, a world in which both great oceans close and an entirely new ocean opens, drawing the land into a cluster near the equator. And the fourth is called Amarcia, a world in which nearly all the continents wander northward and gather in a ring around the Arctic, around the top of the world, leaving Antarctica behind alone at the bottom. Four futures. Four maps, and only one of them, at most, is the world that will actually come to be. We do not know which. We may never know which, because the further you try to run the clock forward, the more the small uncertainties multiply, until a difference too tiny to measure today becomes the difference between one whole world and another 200 million years from now. That is the mystery at the heart of tonight. Not a mystery of the buried past, though we will walk deep into that too, but a mystery of the buried future, waiting patiently on the far side of a gulf of time, so wide that our whole species, everything we have ever built or thought or feared, would fit inside the smallest sliver of it and vanish. And here is the quiet, uneasy thread that runs beneath the wonder, the thread we will follow gently, without alarm, all the way down. When the land last gathered into one, the world it made was not a kind place. The interior of a supercontinent is a hard country, and the models, the careful computer models built by careful scientists, suggest that the next time the land gathers, the world it makes could be harder still, hot enough in its baking heart that the mammals of that distant age, the descendants of everything warm-blooded alive today, might not be able to survive there at all. That is the shadow at the end of this road. But it is a shadow 250 million years away, and we are in no hurry to reach it. We have all the time in the world. We have more time than the world itself will give to almost anything. So before we go any further, a small and simple thing. I always like to know where in the world someone is listening from, lying in the dark, letting these slow stories carry them off. If you feel like it, later, you might leave a note somewhere in the comments telling me what corner of this drifting planet you are resting on tonight. There is something fitting about it, I think, given what we are talking about, all these scattered places that were once joined and will one day be joined again. And if you are new here, if you have only just found this quiet place, you might gently subscribe so that more of these slow journeys can find their way to you on other nights when sleep is far away. That is all. You can do it in the morning. There is no rush. There is never any rush here. Now let us begin to go down. To understand where the land is going, we have to understand the rhythm it moves to, and to understand the rhythm, we have to go back, far back, further than most stories ever dare to go. Because the gathering of the continents into one and their breaking apart again is not a single event that happened once. It is a cycle. It repeats. It has a name, plain and unadorned. Scientists call it the supercontinent cycle. And it is one of the great slow heartbeats of the planet. A pulse so long that no creature could ever live to feel two beats of it, and yet it beats on, faithfully, across the ages. The idea took shape in the minds of geologists over the last half-century, built on the work of researchers like Nance and Worsley and Moody, who looked at the scattered evidence in the rocks and saw a pattern in it, a rhythm hiding in the deep past. And the rhythm goes something like this. The continents drift apart, spreading out across the face of the world, oceans opening between them. Then, slowly, over hundreds of millions of years, the drift reverses. The oceans that opened begin to close. The scattered continents converge, crunching together, raising mountains where they collide, until at last they are all fused into a single great mass, one supercontinent standing alone in one world ocean. And then, because the very gathering of the land traps heat beneath it and stirs the deep interior of the planet, the supercontinent begins to crack. Rifts tear across it. New oceans are born in the cracks. The land breaks apart once more, and the pieces go drifting off again. And the whole slow dance begins over. How long does one full turn of this cycle take? Here the honest answer is a range, not a number. Because the deep past is a blurred and faded thing, and the scientists who study it argue, gently, over the details. But the estimates cluster somewhere between 400 and 600 million years for one complete beat. Some researchers lean toward the longer figure, closer to 600 million years. Others favour something shorter, 400 or 500. Either way, the number is so vast that it dissolves meaning. 400 million years is longer than there have been trees on the land. It is longer than there have been creatures with backbones walking out of the sea. One beat of this planetary heart is longer than the entire history of complex life crawling across the continents. And there have been several beats. The land has gathered and shattered and gathered again, over and over, since long before anything alive could witness it. Let that settle for a moment. The world you know, with its familiar 7 continents scattered across their blue oceans, is not the natural, permanent state of things. It is a passing arrangement, a single frame in an enormously long film. If you could speed the film up so that 100 million years passed in a heartbeat, you would not see continents sitting still. You would see them flowing, streaming across the globe like foam on the surface of something slow and molten, coming together in great clots and pulling apart into scattered flecks, again and again and again, patient beyond all patience, for billions of years. And we happen to be alive in one particular frame, one moment of scattering, halfway between one gathering and the next. That is all. That is where we are. Adrift in the middle of the tide, between two shores of stone. Now, if the land has gathered before, we should be able to find the ruins of those older worlds, and we can, faintly, worn down by unimaginable stretches of time. The first great gathering that most scientists agree upon, the earliest supercontinent, whose existence is fairly widely accepted, has 2 names, because it was pieced together by different researchers looking at different clues, and the reconstructions overlap. Some call it Columbia, some call it Nuna. They are more or less two names for the same lost world. Columbia, or Nuna, came together an extraordinarily long time ago. It began to assemble somewhere around 1.8 billion years ago and finished gathering by around 1.6 billion years ago. Then it held together for a while, a single mass of land in a single sea under a sun a little dimmer than the one we know, and then, around 1.5 to 1.3 billion years ago, it began to break apart, rifting and splitting, the pieces drifting away into a new arrangement. Try to feel the size of that number for a moment, gently, without straining. 1.8 billion years. Not million. Billion. At that time there was nothing on land at all. No plants, no animals, no soil in the sense we would recognize. The land was bare rock, and the seas were home only to the simplest of living things. And already, even then, the continents were performing their slow dance, gathering into one. Nuna was not even the first. Beyond it, further back still, there are older and fainter shadows, proposed supercontinents whose existence grows more and more uncertain the deeper you reach. There is talk of one called Kenorland, perhaps 2.7 billion years ago. And beyond even that, in the very oldest reaches of the record, names like Ur and Valbara whispered from the Archean, the ancient dawn of the world. But the further back you go, the fewer the rocks that survive, and the more the scientists must reason from scraps, and the less certain everyone becomes. So we will not lean too hard on those oldest ghosts. We will simply note that they may be there, dim shapes at the very bottom of time, and that the rhythm of gathering may be older even than we can clearly see. Nuna is where the story grows solid enough to stand on. Nuna is our first firm footing on the long stare down. But here is a question that ought to be nagging at the edge of your mind, softly, as you drift. If the continents are always drifting, always colliding, always being pulled down into the earth at the edges of the shrinking oceans, then why don't they simply wear away? Why doesn't the land get ground down and swallowed and disappear, the way the floor of Pangaea disappeared? Why, after billions of years of this violent, endless rearranging, is there any land left at all? Why can the cycle repeat, over and over, with the same continents gathering and scattering and gathering again? The answer is a beautiful and simple thing, and it comes down to a difference in the rock itself. The Earth's outer shell is not made of one kind of stone. There are two great families of crust. There is oceanic crust, the dark, dense rock that makes the floors of the seas heavy and thin. And there is continental crust, the paler, lighter, thicker rock that makes the land. And the crucial difference between them is weight. Oceanic crust is dense. When it grows old and cold, it becomes heavier than the hot material beneath it, and so it can sink. It can slide back down into the interior of the earth and be swallowed, and this is exactly what happens at the edges of the shrinking oceans, the oceanic floor sliding down and away, sheet after sheet, until an entire ocean like Pangaea is gone. But continental crust is different. Continental crust is buoyant, it is too light to sink. Like a raft of dry wood floating on water, it cannot be pushed down into the depths, no matter how hard the plates crush against one another. When two continents collide, they do not slide over and under each other into oblivion. They crumple. They pile up. They fold and thicken and thrust their edges toward the sky, raising mountain ranges, but they stay at the surface. They persist. And because they persist, because the buoyant land can never be swallowed the way the ocean floor is swallowed, the continents endure across billions of years. They are shuffled and rearranged, split and rejoined, worn low and lifted high, but they are not destroyed. The same ancient rock rides on, from one supercontinent to the next, from Nuna to whatever comes after, carrying the deep memory of the world in its crystals. That is why the cycle can repeat. That is the physical reason the land keeps coming back together. The continents are permanent passengers on a restless planet, unsinkable rafts on a sea of stone, drifting apart only to be gathered up once more. And it means that some of the rock beneath your feet tonight, or beneath the feet of someone far away who is also listening in the dark, is unimaginably old. It has been part of continents that no longer exist. It floated in Nuna more than 1 billion years ago under a fainter sun, in a world with no life upon the land. It has been on a journey longer than life itself, and it is still going, still drifting, still being carried at the speed your fingernails grow toward the next gathering of the world. So when Nuna broke apart, around 1.5 billion years ago, the buoyant fragments of it did not vanish. They scattered and drifted and wandered the face of the planet for a few 100 million years, each carrying its ancient stone, each riding the slow currents of the deep earth. And then, on the beat of the cycle, faithful as ever, they began to feel the pull toward one another once more. The oceans between them began to close, the scattered pieces began again to converge. And out of that gathering, out of the slow reunion of the fragments of Nuna, the next great supercontinent would be born, and it would carry a name that many geologists regard as the most complete and well-established of all the ancient gathered worlds. But that is a story for the next part of the descent, and there is no need to reach for it yet. For now it is enough to hold, softly, the shape of what we have found. That the ground is moving, always, too slowly to feel. That whole oceans open and close and vanish. That the land gathers into one and breaks apart and gathers again, on a rhythm 400 to 600 million years long. A rhythm that has beaten since the deep dawn of the world. That the first firm gathering we can name is Nuna, 1.8 billion years old. And that the continents endure through all of it because they are too light to sink, buoyant rafts of ancient stone that can never quite be lost. There is a strange comfort in it, I think, if you let there be. All the things that feel so fixed, the coastlines, the mountains, the map on the wall, are only passing shapes, frames in a film too slow to see. Nothing is standing still. Everything is drifting, gently, toward somewhere else. And you, lying here in the warm dark, are drifting too. On your own small raft of stone, at the speed your fingernails grow, toward a gathering of the world that no living eye will ever see. There is nothing to fear in it. It is only the tide. It has been coming in and going out since long before us, and it will go on long after, and tonight, for a little while, we get to lie here and listen to it move. Let your breathing slow to match it. In and out. Oceans opening, oceans closing. The land drifting home across the ages. And we will keep going down, slowly, gently, into the deep past, following the ancient continents as they gather and scatter and gather again, all the way toward that distant, baking, unknowable world that waits at the far end of time. But there is no hurry. There is never any hurry here. We have 400 to 600 million years, and the whole of the dark, and all the drifting stone in the world, and we will take it slowly, one soft beat of the planet's heart at a time. So stay with me, if you can, and if you drift off before we reach the end, that is exactly as it should be. The story will still be here, the continents will still be moving, and we will simply keep going down together into Rodinia and the ancient ice and the great gathered world of Pangaea and everything that came after, one slow breath at a time. And here is where it begins, tonight, in one particular place, so slowly you would never feel it if you stood on the very seam of it. Down the middle of the Atlantic, along a ridge of undersea mountains that runs from the far north to the far south, the ocean floor is splitting apart and new stone is welling up to fill the gap. And the two halves of the world are drifting away from each other at the speed a fingernail grows, 2, perhaps 4 centimeters in a year. You could not watch it. You could stand there for your whole life and see nothing. But give it 100 million years, give it 200, and those quiet centimeters become an ocean widening, and somewhere on the far side of the planet, to keep the balance, another ocean must be closing to make room. And it is. The great Pacific, the last living remnant of a far older sea, is shrinking. Its floor is sliding down into the deep places of the earth around its rim, vanishing back into the mantle it came from, a few centimeters at a time, the same slow currency as everything else here. The land is not lost when it moves. The sea, though, the sea can be swallowed whole. That has already happened once, to an ocean larger than any we know now. Around the last gathered world, around Pangaea, there stretched a single global ocean called Panthalassa, vast beyond imagining, wrapping almost the entire planet in one unbroken body of water. And it is gone. Its floor has been drawn down into the earth, almost in its entirety, subducted, recycled, erased, so that the sea that once covered most of the world now survives only as a shrinking fragment we call the Pacific. An entire ocean can disappear. Hold that quietly for a moment in the warm dark. The water that seems the most permanent thing of all, the thing we measure the land against, is itself only passing through. Oceans open. Oceans close. And the map you learned as a child is not the map your distant descendants would find, if any distant descendants there are to find it. Which brings us to the strange and honest heart of tonight's story, the thing that makes it a mystery and not a prophecy. Because the truth is that nobody knows exactly which future map is real. Nobody can say for certain how the continents will choose to gather. And nobody can promise you which of the several possible worlds is the one that will actually rise from the closing seas. There are 4 of them, 4 different futures, each with a name, each drawn by careful people staring into the deep time ahead, and they do not agree. There is Pangaea Ultima, sometimes called Pangaea Proxima, in which the Atlantic itself closes back up and all the land regathers around Africa. There is Novo Pangaea, in which the Atlantic keeps widening, and it is the Pacific that finally shuts, drawing the continents together on the other side of the world. There is Orica, in which both oceans close and a wholly new sea is born, and the land clusters down along the equator. And there is Amasia, in which the continents wander northward instead, gathering around the top of the world, around the Arctic, leaving Antarctica behind alone at the bottom. 4 worlds, 4 gatherings, and we will walk toward all of them, slowly, in the nights and the hours ahead, and I will not pretend to you that I know which one is coming, because no one does. And that not knowing is part of the beauty of it. Before we go down into it, let me ask you one small, warm thing, the kind of thing I like to ask before a long journey. Wherever you are lying tonight, whatever corner of the world holds you in the dark, tell me. Leave a word in the comments and say where you are listening from, what city, what country, What quiet room? Because there is something I find deeply comforting in knowing that this slow story is being carried into so many different nights at once, across so much of the very drifting land we are talking about. And if you are new here, if you have only just found your way into these long, slow descents into deep time, then settle in and subscribe so the next one finds you when you need it. That is all. That is the only thing I will ask of you tonight. The rest is just the story, and the dark, and the long way down. So here is the promise I make you plainly before we begin. Tonight, and across the parts that follow, we are going to walk the entire span of it, from the very first time the continents gathered into one, more than 1.5 billion years ago, all the way forward to that distant, baking, half-known world that waits some 250 million years ahead, the one that could bring the age of mammals quietly to its close. We will take it slowly. We will not rush a single age. And you may fall asleep at any point along the way, in any age you like, and lose nothing at all, because the ground will keep moving whether you are awake to feel it or not. Let us begin where the pattern itself begins, because this is the thing to understand first, the thing that makes all the rest possible. The gathering of the continents is not a single event that happened once, long ago, in Pangaea. It is a rhythm. It is a cycle, a slow heartbeat of the whole planet, in which the land draws together into one great mass, and then breaks apart, and drifts, and then, after an unimaginable span, draws together again somewhere else. Geologists call it the supercontinent cycle, and its beat is long, longer than almost anything else we measure, something on the order of 400 to 600 million years from one gathering to the next. People spent a long time learning to hear it. The idea took shape through the careful work of scientists like Nance and Worsley and Moody, who read the scattered rocks of the world and began to see, buried in them, the same slow pulse repeating, the same coming together and coming apart, over and over, deeper into the past than anyone had thought to look. Once you know the beat is there, the whole history of the earth begins to sound less like a straight line and more like breathing. In and out. Land gathering. Land scattering. Again and again and again. And it has happened that we can trace, at least 3 times. The first great gathering we can name with any confidence rose more than 1.5 billion years ago, in a world so ancient there were no plants on the land, no animals anywhere, nothing but bare stone and shallow seas full of the simplest life. We call it Columbia, and we also call it Nuna. 2 names for overlapping glimpses of the same lost world, assembled somewhere between 1.8 and 1.6 billion years ago. It held together for a long, long time, hundreds of millions of years, one gathered mass of barren continent under an empty sky, and then, around 1.5 to 1.3 billion years ago, it too began to break apart, the way they all do in the end, splitting and drifting and scattering back out across the face of a younger Earth. The first gathering. The first breaking. The opening beat of a rhythm that is still playing tonight. Beneath your bed, beneath the ocean, beneath everything. And here is the quiet reason it can happen at all. The reason the land can gather and scatter and gather again without ever being destroyed. The continents are made of a lighter stone than the ocean floor. Continental crust is buoyant. It floats, in a sense, high and stubborn upon the heavier mantle beneath, too light to be pulled down and swallowed the way the ocean floors are swallowed. The seas may vanish, drawn into the deep and recycled away, but the continents endure. They are pushed and dragged and cracked and carried halfway around the world, but they are not erased. They persist. And because they persist, they can always be gathered up again. The same ancient stone rearranged into a new and unfamiliar world, drifting slowly home across the ages to a reunion no eye will ever see. So the rhythm continued. So the slow tide went on. After Columbia and Nuna had scattered their pieces back out across the empty ocean, the planet did not rest in its dispersal. It never does. The same forces that had gathered the land once began, patiently and without hurry, to gather it again. Mantle heat still moved in those vast, sluggish currents deep beneath the crust, carrying the plates above them the way a river carries a leaf, slowly, imperceptibly, irresistibly, and over hundreds of millions of years the scattered remnants of the first assembly drifted and turned and pressed together once more, suturing along great mountain ranges that no one alive has ever seen, building the second great supercontinent on a world that was still, in many ways, almost unrecognizably old and strange. We call it Rodinia. The name comes from the Russian word for homeland, and there is something fitting in that, something that resonates even now, because Rodinia was, in a sense, a second homecoming, a second gathering of everything the planet had to offer into a single embracing mass. It assembled through what geologists call the Grenville orogeny, a collision event so large and sustained, so continent-wide, that the mountain ranges it produced would have dwarfed even the modern Himalayas, ranges of folded and upthrust rock running thousands of kilometers across the face of the late Precambrian world, thrown up as cratons drove into one another at the grinding pace of centimeters per year. That assembly was largely complete somewhere around 1.1 to 900 million years ago. Think of that number quietly. 900 million years ago. Animals had not yet evolved. Not a single multicelled creature with legs or fins or eyes had yet appeared anywhere on the face of this earth. Rodinia existed in a world of microbial mats and shallow chemical seas, a world of bare dark rock and iron-red sand, and a sky with a slightly different colour to the light. The sun younger and a little dimmer, the days shorter, because the planet's spin had not yet slowed quite as much as it has now. And across all that strange and vacant landscape, the supercontinent sat like a knot at the centre of a vast, encircling ocean. It held together for a long time, as they tend to do. The gathering takes hundreds of millions of years, and the holding can last hundreds of millions more, and then, always, in the end, the heat that had been trapped beneath the joined landmass, all that internal warmth, with nowhere to escape, began to do what it always does. It built up, and spread, and lifted, and the crust above it domed and cracked, and opened along great rifts that tore the supercontinent apart. Beginning somewhere around 750 million years ago, and continuing in pulses and surges through to roughly 600 million years ago. Rodinia broke into pieces. The pieces drifted. And here is where the story takes the first of its quiet, astonishing turns. Because, when Rodinia broke apart, the world did not warm. It froze. Not a little, not in the way we think of an ice age, with glaciers spreading down from the poles while the tropics remain habitable and green. The world froze almost completely. The glaciations of the Cryogenian period, the interval from roughly 717 to 635 million years ago, an interval geologists sometimes call, with a certain geological bluntness, Snowball Earth, were among the most extreme climate events in Earth's entire history. Ice appears to have reached the equator. The ocean surface may have been largely frozen over. The planet, in other words, came within measurable distance of a runaway freeze, a condition from which recovery might have been extraordinarily difficult or perhaps impossible. Had the carbon dioxide from volcanic activity not slowly built up beneath those ice-covered seas and eventually tipped the balance back toward warmth? Now, the same process. The same broad class of event, continental assembly and then breakup, plates in motion, oceans opening and closing, the deep machinery of the planet doing what it does. And yet the outcome was, by almost any measure, the precise opposite of what the models project for Pangaea Ultima and the distant future. Not a hothouse. A deep freeze. The same cause and the other extreme. This is worth sitting with for a moment, because it is the kind of thing that could tempt you to think the whole story is too uncertain to take seriously, that the science points in every direction at once. But it does not. The reason the outcomes diverge so dramatically, Rodinia's breakup leading to ice, the future assembly projected to lead to heat, is not a contradiction in the science. It is the science working exactly as it should, sensitive to initial conditions, to the position of the continents, to the chemistry of the atmosphere, and, most crucially, to the brightness of the sun. When Rodinia broke apart 700 million years ago, the sun was measurably dimmer than it is today. It has been brightening all along, slowly and steadily, a fraction of a percent every tens of millions of years, following the physics of stellar aging as naturally and inevitably as a fire settling into its coals. 700 million years ago, the sun delivered roughly 6 or 7% less energy to the Earth than it does now. That gap may seem small, but on a planet whose climate is finely balanced, where the difference between a world of ice and a world of jungle can hinge on changes measured in fractions of a degree over centuries, a shift of several percent in the solar constant is enormous. The cryogenian Earth was working against a dimmer engine. When Rodinia's breakup exposed fresh rock to the atmosphere, great new coastlines of silicate stone, available to be weathered by rain and dissolved by carbonic acid, drawing carbon dioxide out of the air, the reduced volcanic activity of a fragmenting continent, combined with that aggressive weathering drawdown, could pull enough CO2 from the atmosphere to tip an already cool world into ice. The silicate weathering thermostat is what geologists call this slow chemical process, and it is one of the most beautiful mechanisms on the planet. Rain falls. It picks up a small amount of carbon dioxide from the atmosphere, forming a weak carbonic acid. That acid touches rock, granite, basalt, the continental stones exposed by erosion, and it reacts with the silicate minerals there, drawing the carbon down out of the air and eventually washing it, dissolved into calcium carbonate and other compounds, into the sea, where it settles to the seafloor and is locked away. Over millions of years, this process acts as a genuine thermostat, pulling the planet cooler when CO2 is high and temperatures allow rain to reach exposed rock, and warming again when volcanism adds more CO2 to the air and the rock is buried or submerged. Rodinia's breakup, with its extensive new coastlines, seems to have turned this thermostat toward cold, at a time when the sun was already not supplying the extra warmth it would later deliver. Pangaea Ultima will form when the sun is brighter, and the configuration of that future supercontinent, a vast interior sealed from the moderating influence of the ocean, will suppress the very silicate weathering that might otherwise provide a cooling break. The two situations are not contradictory. They are, in fact, the same machine running under different conditions, delivering different results, the way the same river can flood a valley in one season and leave it cracked and dry in another. The cryogenian ice did eventually end. Carbon dioxide from ongoing volcanism, released even beneath the frozen ocean crust, accumulated in the atmosphere over millions of years without the normal weathering process to remove it. Because the ice itself had buried and frozen the reactive rock surfaces that the thermostat depends on, and eventually the greenhouse warming overcame the reflectivity of all that ice, and the planet thawed dramatically and rapidly in geological terms. Out of that thaw came something remarkable, the Ediacaran period, the first geological window in which large, soft-bodied multicelled organisms appear in the fossil record in abundance, strange and alien things that look nothing like any animal alive today, quilted and frond-like, and immobile and strange. Life was preparing to become complicated. The world was preparing for something genuinely new. And somewhere in that interval, around 633 to 573 million years ago, there may have been another supercontinent. Its name is Pangaea. And the honest thing to say about it, the thing that the science genuinely requires, is that its existence is contested. Some geologists see the evidence for a brief, temporary assembly of the scattered pieces of Rodinia into a new and shorter-lived gathering during the Ediacaran, a kind of gathering before the gathering that lasted perhaps a few tens of millions of years before dispersing again. Others argue that the evidence does not quite support calling it a true supercontinent, that it was more of a loose congregation. Pieces close together without fully joining. A near assembly rather than a genuine one. The reason to name it here, even with that honest flag of uncertainty, is not to add a false number to the count, but because it is part of what the rock record is quietly trying to tell us, that the supercontinent cycle is not a perfectly metronomic clock. Not a mechanism so regular you could set your watch by it, but a long rhythm with variations and interruptions and contested episodes, the kind of deep time rhythm that accumulates over billions of years and which we are still in the process of learning to read. And then the pieces gathered again, more completely, more definitively, in the assembly that most of us have at least heard the name of. The one that left its silhouette pressed into the rocks of every continent on Earth. The one whose ghost still haunts the shape of the ocean basins, the mountain ranges, the sedimentary sequences laid down in its interior. Pangaea, its assembly was long and complicated, the work of hundreds of millions of years and multiple distinct collision events, plates driving into one another in sequence. Suturing and crumpling and building ranges of mountains the way a tablecloth bunches when you push it across a table. The Appalachians in North America, the ancient and worn-down mountains of Scotland, the ranges of Scandinavia, all of these are remnants of those collisions, the eroded stumps of ranges thrown up when the continents of the Paleozoic world pressed together. The assembly was largely complete somewhere around 335 to 300 million years ago during the Carboniferous and early Permian periods, an era when the world was warm and humid and the first forests were laying down the carbon deposits that we would eventually mine as coal. A world with insects the size of birds, with vast equatorial swamps, with a land surface joined into one sprawling body. Pangaea, the name, means all earth, and it was, in the most literal sense, all the earth there was. One continent, not a cluster of continents separated by narrow seaways, as in the Carboniferous assembly's early stages, but an eventually fully joined single mass, stretching from pole to pole, wider at some latitudes than any landmass today. An unbroken span of rock, from what would become Antarctica all the way north to what would become Siberia, from what would become Western North America all the way to what would become the eastern edges of Asia. The surrounding ocean was Panthalassa, a name that means all sea, and it was that, an enormous, largely continuous global ocean covering nearly everything that was not Pangaea. Stretching 3/4 of the way around the world at the equator, an ocean so vast that most of its ancient floor is now completely gone, subducted back into the mantle over the hundreds of millions of years since Pangaea began to break apart. You cannot visit the Panthallassic seafloor. It does not exist anymore. The ocean that once surrounded all the land on Earth has been swallowed by the same process that will eventually close the Atlantic, drawn down into the mantle, melted, recycled, gone. The Pacific Ocean today is its shrinking remnant, still enormous, still the largest body of water on the planet, but a fraction of what Panthalassa once was. And within Pangaea, in its eastern side, there was a great enclosed bay or sea, the Tethys, a broad, warm body of water that cut into the supercontinent from the east like a deep embrace, its shallow tropical reefs eventually becoming the limestone of the Alps, the Himalayas, the rocks of what is now Turkey and Iran and Central Asia. The Tethys was a remnant that persisted long after Pangaea itself began to break apart, slowly shrinking as Africa drove northward and India raced home to its collision with Asia. Until today, all that remains of it is the Mediterranean Sea, a puddle, by comparison, the last landlocked remnant of an ocean that once stretched from Gibraltar to Southeast Asia. When you look at the Mediterranean on a map, you are looking at the closing wound of the Tethys, still slowly narrowing as the African plate continues its patient northward drift. But here is what Pangaea did to the climate of its interior, and this is the mechanism that matters for what is to come. Not the oceans, not the seas, but the dead. Baking. Airless centre of a continent so large that its heart was sealed from any coastal influence for distances measured in thousands of kilometres. The continents we live on today have interiors, too, the middle of Asia, the centre of North America, the interior of Australia. These places are already more extreme than the coasts. Drier, hotter in summer, colder in winter, because they are cut off from the moisture and the moderating influence of the sea. The ocean is a thermal buffer. It absorbs heat in summer and releases it in winter. It evaporates water into the air that falls as rain. It keeps the temperature swings within a range that most life can navigate. But the further you go from the coast, the less of that moderation you receive, and the more extreme the climate becomes. Geographers have a name for this effect, continentality. And Pangaea, being by definition the largest continent that has ever existed, would have expressed continentality on a scale that today's continents can only hint at. The evidence is in the rocks. The sedimentary sequences deposited in Pangaea's interior during the Permian and Triassic, the periods during which the supercontinent was at its fullest extent, are filled with red beds and evaporites. Red beds are sedimentary rocks stained red by iron oxide, by the rusting of iron bearing minerals in highly oxidized, seasonal, arid conditions. Evaporites are the mineral deposits left behind when shallow lakes or seas evaporate completely, leaving their dissolved salts and minerals crystallized on a dry basin floor, beds of rock salt, gypsum, anhydrite, the chemical signatures of a landscape where water arrives infrequently and leaves quickly, pulled away by heat and dryness before it has a chance to linger. These rocks are the diary of the Pangaean interior. They record, in the patient language of mineral chemistry, a landscape of vast deserts, seasonal extremes, and intense aridity spreading across millions of square kilometers of the supercontinent's heart. There was also something that the models have recovered, and the rock record partially supports: a mega monsoon. Imagine the monsoon seasons of the modern world. The great seasonal reversals of wind and moisture that bring rain to the Indian subcontinent, to West Africa, to Southeast Asia each summer, driven by the temperature difference between the heating land and the cooler sea. Now imagine that same process operating on a continent several times larger than any we have today. A continent that heated its interior to extraordinary temperatures each summer, pulling air masses inward from the surrounding Panthalassic Ocean in enormous swirling circulation patterns, delivering intense and concentrated rains to the coastal margins while leaving the deep interior in perpetual shadow of an inverse kind, too far from any coast for those rain belts to reach. Too large for the monsoon circulation to penetrate, sealed inside a ring of its own making. The mega-monsoon of Pangaea, as climate models reconstruct it, would have been unlike anything alive today. Wet seasons of violent intensity along the outer margins, a dead, baking, windswept heart. This is not a projection about the future. This is an inference about the past, made from rocks from the actual sedimentary record of what Pangaea left behind. The future supercontinent Pangaea Ultima, when the models project temperatures of 40 to 70 degrees Celsius across its interior, are drawing on a mechanism that has a demonstrable rock-recorded precedent. Not in a model alone, in the actual fossil stone of the actual planet we are sitting on. And now, before we follow that thread forward into what the models say Pangaea Ultima might do, before the three converging clocks are set in motion and the full weight of what is projected for that distant world is laid out, it is worth pausing to ask the question that should, by rights, have come much earlier. The question that lurks behind all of this ancient history like a shape at the edge of a darkened room. How do we know any of this? How does anyone look at a slab of rock laid down 900 million years ago, or 300 million years ago, or 2 billion years ago, and say with any confidence this was part of a supercontinent? These mountains were built here. These stones were once half a world away. The answer is several things at once, because reading deep time requires multiple lines of evidence that have to agree before geologists feel confident enough to publish a reconstruction. There are the magnetic signatures locked into ancient rocks, iron-bearing minerals that crystallized at high temperatures and, as they cooled, aligned themselves with the magnetic field of the Earth at the moment of their solidification, preserving a record of where the rock was in latitude when it formed, like a compass needle frozen in stone. There are the matching fossil assemblages on continents now separated by thousands of kilometers of ocean, the same species of ancient fern or reptile found in Brazil and in West Africa, in India and in Antarctica, species that could not have swum the modern ocean and whose presence on now distant shores can only be explained by the land once being joined. There are the matching geological provinces, mountain belts of the same age and same rock type that line up across the modern Atlantic, like two halves of a torn page, proving they were once one continuous range. But for the oldest supercontinents, for the deepest time, for the assemblies so ancient that the rock record becomes fragmentary and the magnetic signatures are overprinted and altered by metamorphism and heat, there is something more specific, something almost surprisingly small, given the scale of what it is used to reconstruct. A zircon crystal. Zircon is a mineral, zirconium silicate if you want the chemistry, and it crystallizes in very high temperature environments, in magmas and in the roots of mountain ranges where rock is being metamorphosed under enormous heat and pressure. And when it crystallizes, it incorporates uranium into its crystal structure but excludes lead almost entirely. This matters enormously, because uranium decays to lead at a known, constant rate, a rate that does not change with temperature or pressure or chemistry, a rate that the physics of radioactive decay sets and nothing in the Earth can alter. So a zircon crystal is in effect a clock. It starts at zero lead when it crystallizes, and from that moment forward, lead accumulates as the uranium decays steadily and reliably for as long as the crystal survives. And zircon is extraordinarily tough. It can survive metamorphism, erosion, transport, redeposition, more metamorphism, more erosion. It is one of the most durable minerals on the planet. Ancient zircon crystals, their original character preserved across billions of years, can be found eroded out of their source rock and deposited as detrital grains in much younger sedimentary rocks, sitting among sand grains in a river delta laid down 1 billion years after the zircon itself was born. What geologists look for in the sedimentary rocks associated with ancient mountain belts and supercontinent assembly events is patterns in those detrital zircon ages. When a supercontinent assembles, it drives enormous mountain-building events, orogenies in the technical language, and those orogenies produce vast quantities of new zircon, crystallizing in the heated roots of the colliding mountain ranges. Those zircons eventually erode and are carried downstream into the sedimentary basins surrounding the mountains, mixed into the rock record as a characteristic pulse of ages. Detrital zircon age peaks, they are called, concentrations of zircon grains of a particular age found in sedimentary rocks from that era. Their ages measured by uranium-lead ratios and their distribution plotted as a histogram that shows the geologist exactly when great mountain-building events, and by inference, great continental collisions, occurred, the Grenville orogeny, the event that assembled Rodinia roughly 1.1 to 900 million years ago, is named and defined in large part by exactly this kind of evidence, a characteristic peak in detrital zircon ages found in sedimentary rocks on multiple present-day continents, a shared fingerprint of collision preserved in the mineral record and only explicable if those continents were once pressed together, building mountains together, shedding zircon together into basins that the erosion of 1 billion years has since scattered to different corners of the globe. The rocks remember, even when nothing else does. The crystals carry the timestamp, and by reading those timestamps across enough rock samples from enough continents, geologists can begin to reassemble the lost maps, to sketch the outlines of supercontinents that have been gone longer than complex life has existed, to put names to worlds that will never be directly seen, Nuna, Rodinia, Pangaea, perhaps, in some form. Pangaea, most certainly. Each one assembled, each one held, each one broke apart in the end, the trapped heat always winning over the gathered mass. The rifts always finding their way through the weakest points in the thickest stone, the ocean always returning to fill the spaces the breaking created, the Wilson cycle turning once more in the deep interior of a planet that is, in this regard, quietly and endlessly patient. J. Tuzo Wilson was a Canadian geophysicist who recognized, in the 1960s and 70s, that ocean basins go through a cycle of their own, that they open along rifts, widen through seafloor spreading, and then eventually close again as subduction overtakes the spreading, before finally colliding the continents on either side into a new mountain range, and then, perhaps, rifting open again along approximately the same line. He named this the Wilson cycle, and it is the ocean-scale version of the supercontinent cycle, the detailed mechanism underlying the grand rhythm. A single Wilson cycle, from rift to ocean to collision and back to rift, takes somewhere on the order of hundreds of millions of years, nested inside the longer supercontinent rhythm the way a wave is nested inside a tide. The Iapetus Ocean, a predecessor to the Atlantic, occupying broadly the same space between what would become North America and what would become the British Isles and Scandinavia, opened, widened, and closed again before the Atlantic ever began to open. Its closure is what built the Appalachians and the Caledonides, the ancient mountain chains of eastern North America and the British Isles. And then the rifting began again, along approximately the same zone of weakness, and the Atlantic opened in its place, and here it is now, still widening, still young, the successor ocean in the same line as the one that preceded it. The Rheic Ocean opened after the Iapetus closed. It too closed, contributing to the assembly of Pangaea. The Tethys Ocean opened within Pangaea's body and then narrowed as the continents on either side of it converged. The Panthalassic Ocean, the great surrounding sea of the Pangaean world, shrank as Pangaea grew, and now its remnant, the Pacific, is still shrinking, still being consumed at its margins by subduction zones that ring it on nearly every side, the so-called Ring of Fire, where the ocean floor bends down and dives back into the mantle, where earthquakes are frequent and volcanoes mark the line of return. Ocean basins open and close, continents gather and scatter. The Wilson cycle turns, and the supercontinent cycle turns above it, a larger wheel driven by the same engine. Pangaea's interior, sealed by the sheer scale of its own mass, baked by the continentality effect, traced by red beds and evaporates, and the ghost of a mega-monsoon, was, by any measure, a difficult environment for life. Not uniformly so. The margins, the coasts, the places where moisture from the surrounding ocean could still reach the land, were habitable enough, lush enough in places. The equatorial belt, where the Tethys penetrated the supercontinent's eastern side, offered warmth and moisture in combination. The Permian world, while harsh in the interior, sustained rich ecosystems in its more favoured regions. The coal swamp ferns of the Carboniferous had given way to a different flora, and the vertebrate fauna of the Permian included the ancestors of both the mammal lineage and the reptile lineage, the synapsids and their kin moving through a world that was already, in some interiors, extreme. And then came the end of the Permian. But that belongs to a later part of this descent, to the moment when the three converging clocks are set before you, and the full weight of what the models project for a world 250 million years away is laid out slowly and carefully, the way a guide lays out a map on a table before a long journey. For now, let it be enough to know that Pangaea was real and large and capable of baking its own heart. Let it be enough to know that the Wilson cycle turns, and that the Atlantic Ocean, whose widening you cannot feel, but whose geometry you can hold in your mind, the jigsaw puzzle fit of South America and Africa, the spreading ridge running down its centre like a seam, is following the same pattern that has played out before, and that the question of whether it will eventually close again, the question of whether Pangaea Ultima or some other assembly will eventually emerge from that closing, is not a question of science fiction, but a question of timing and mechanism of which forces will prove dominant in the very long run. The zircons remember what the open ocean has long since swallowed. The red beds record what the continentality of the past imposed on the living things of the interior. The detrital age peaks tell the story of mountains that have been worn to roots, of collisions that happened before any eye existed to see them, of a planet that has been rearranging itself since long before it carried anything we would recognize as complex life. And it is still rearranging, slowly, at the pace of your fingernails growing, but without pause. So the question is worth staying with a little longer. The question of how, exactly, a continent moves. Not the fact that it moves, that much is now beyond serious dispute, the GPS stations confirming what the paleomagnetism and the fossil distributions and the zircon age peaks had already told us, but the mechanism, the actual physics. The reason a plate of rock weighing something beyond any ordinary number you could hold in your head is in motion at all, and has been in motion for billions of years, and will continue in motion for hundreds of millions of years more, grinding forward at a pace that seems almost contemptibly slow, and yet, measured across the right timescales, amounts to the complete rearrangement of everything. The first thing to understand is that the mantle, that vast shell of rock between the thin crust you stand on and the iron core at the center, is not liquid in the way that water is liquid, and not solid in the way that the ground beneath a house is solid. It is something in between, something that would shatter if you struck it with a hammer and yet flows, over millions of years. The way very thick tar flows, the way a glacier flows, almost imperceptibly but with immense, patient force. And it flows because the centre of the earth is hot, extraordinarily hot. Hot partly because of the heat left over from the planet's violent formation, when rock and ice and metal fell together out of the early solar system in collisions that released enormous energy. And hot partly because of radioactive decay, uranium, thorium, potassium, atoms whose nuclei are slowly and continuously breaking apart inside the rock of the mantle, releasing heat as they do, the way a small ember radiates warmth even when you cannot see it glowing. That heat has to go somewhere. And it does. It rises, not quickly, not dramatically, but steadily, in great slow convective loops, hot material welling upward beneath the mid-ocean ridges, cooler material descending elsewhere, the whole mantle churning in a pattern of circulation that is, in principle, not so different from what happens when you heat a pot of thick syrup on a stove, the warm material rising in the centre, the cooler material sinking at the edges, the whole slow circulation driven by nothing more than the fact that heat rises and cold descends. This is mantle convection, and it is one of the engines of the whole cycle. But it is not the only engine, and some researchers would argue it is not even the dominant one, because there is another force at work in the system. One that is in some ways more intuitive once you picture it clearly, and that force is called slab pull. Imagine the oceanic plate, not the continental crust, which is thick and light and buoyant, made of granite and related rocks that float on the mantle the way a cork floats on water, but the oceanic crust, which is thinner and denser, made of basalt and gabbro, heavier, less buoyant. Oceanic crust is young, at least in geological terms. It is created continuously at the mid-ocean ridges, the spreading centres, where the mantle wells up and solidifies into new rock, pushing the plates apart. And as it moves away from the ridge where it was born, it cools, it contracts, it becomes denser. And after tens or hundreds of millions of years of travelling across the ocean floor, it arrives at the far side and encounters either another oceanic plate or the edge of a continent, and because it has become denser than the mantle beneath it, it begins to sink. This is subduction. The plate bends and descends into the mantle, returning to the depths from which it came, completing a circuit that can take 100 million years or more. And here is the slab pull part. As the leading edge of the plate sinks into the mantle, growing colder, growing denser, pulled inexorably downward by gravity, it drags the rest of the plate behind it. The way a tablecloth, if you let one edge slide off the table, would pull the rest of the cloth toward the edge. The descending slab is heavy, and it exerts a tension on the plate above it, a pull, and that pull appears to be the dominant driver of plate motion on present-day Earth. The ridge push, the force exerted by the elevated hot material at the mid-ocean ridges, pushing outward from the centre of spreading, adds to the system as well. A gentler shove from behind to complement the insistent drag from ahead. But slab pull does most of the work. The sinking of old cold oceanic crust is the engine that keeps the whole surface of the planet in motion. And this matters for the question of what comes next. Because the way a supercontinent assembles depends critically on where the subduction is happening. Which oceans are losing floor to the mantle, which are growing, and which will eventually be consumed entirely. The Atlantic Ocean is growing. The mid-Atlantic ridge is adding new seafloor continuously, pushing the Americas westward and Europe and Africa eastward, and the rate of that spreading, a few centimetres a year, comparable to the rate your fingernails grow. A rate you cannot feel, but a rate that over 250 million years adds up to thousands of kilometres, is something you can measure today with extraordinary precision. The GP satellites confirm it. The seafloor magnetic stripes record it in layers of alternating polarity, the way a tape recording captures sound. Except that what is recorded here is the history of the Earth's reversing magnetic field, laid down in basalt as each new strip of ocean floor solidified at the ridge. But the Pacific Ocean is shrinking. The vast ancestral ocean, the descendant of Panthalassa that once surrounded Pangaea, is being consumed by subduction zones all around its rim, the Ring of Fire. The long chains of volcanoes and earthquakes from New Zealand up through the western Pacific, through Japan and Kamchatka, around to Alaska, down the western coast of the Americas. All of it marking the places where Pacific oceanic crust is bending downward into the mantle. All of it the edge of an ocean that is, in a very real sense, being swallowed. The Pacific is perhaps 100 million years or so from being entirely consumed, depending on the model, depending on the rates, depending on factors that are genuinely difficult to predict with precision. But the trend is clear. The Pacific is going. Now here is the question that geologists and climate scientists and geodynamicists have spent considerable effort debating. And that is the question of what happens after that. If the Pacific closes first, if the great ring of subduction zones around it pulls the surrounding continents toward the center faster than any new dynamics emerge elsewhere, then the Americas would eventually drift westward and collide with Asia and Australia, and a new supercontinent would form, broadly, over what is now the Pacific Basin. This is the extraversion model. The continents turn themselves inside out, so to speak. They gather not where Pangaea was, but on the opposite side of the planet, over the floor of the ocean that is now the largest on Earth. The name given to this possible future is Nova Pangaea, and it is one of 4 serious contenders for the title of the next supercontinent. But there is another possibility. The Atlantic is young, as oceans go. It began opening only about 200 million years ago, during the breakup of Pangaea. It is still in what geologists sometimes call its youth, still widening, still building new seafloor at the mid-Atlantic ridge. But the Wilson cycle, named for J. Tuzo Wilson, the Canadian geophysicist who first articulated the idea that oceans open and close on geological timescales, suggests that what opens must eventually close. An ocean that is spreading now may, under the right conditions, begin to subduct. A new subduction zone might initiate along one of its passive margins, the quiet, trailing edges of continents that currently border the Atlantic. And once subduction begins and the slab pull takes hold, the dynamic can reverse. The Atlantic, which opened when Pangaea broke apart, might close again, driving the continents back together roughly where they started, reassembling a supercontinent in more or less the same neighborhood as the original. This is the introversion model. The world turns inward on itself, and the future supercontinent produced by this scenario is the one you may have heard of, the one whose name carries the most weight in popular accounts of this subject, the one that some researchers associate with consequences severe enough to challenge the survival of mammals. Pangaea Ultima. Christopher Scotese, the American paleogeographer who has spent decades mapping the history and future of the continents through his Paleomap project, is perhaps the researcher most closely associated with this scenario. His reconstructions have given many people their first coherent visual picture of where the continents have been and where they might go, and the name Pangaea Ultima, which he has also referred to as Pangaea Proxima, preferring the latter because it avoids the implication that this would be the final supercontinent, the last one the Earth would ever form, suggests a future roughly 250 million years from now, in which the Atlantic has closed, Africa has pushed northward and collided with Europe, the Mediterranean has been entirely consumed. The Americas have drifted and rotated and pressed themselves against the assembled mass, and a new supercontinent sits astride the planet, vast and hot and, according to the most detailed climate models yet applied to it, barely survivable for creatures like us. 250 million years. It is worth sitting with that number for a moment. It is, as it happens, almost exactly the same distance into the future as the end Permian extinction is into the past. That catastrophe, the largest extinction in the history of complex life, the one that eliminated something like 90% of marine species and 70% of terrestrial vertebrate species, the one that came closer than any other event to erasing the entire experiment of animal life on this planet, happened approximately 252 million years ago, on Pangaea, on a world that was already assembled into one vast landmass, when the Siberian traps began erupting and the CO2 began to rise, and the warming spiraled into something that the biosphere could barely survive. The same span of time that separates us from that catastrophe separates us from the projected assembly of the next one. There is a kind of symmetry in that, a kind of geological rhyme, but the honest answer to the question of which of the 4 named futures is actually correct is that no one knows, and the uncertainty is genuine, not provisional. Beyond roughly 50 to 100 million years, the extrapolation of plate motions becomes increasingly speculative. The forces that will determine whether the Atlantic eventually develops new subduction zones, or whether the Pacific closes first, or whether some combination of dynamics produces something else entirely, are too complex and too sensitive to initial conditions to model with confidence at the scale of 250 million years. And so alongside Pangaea Ultima and Nova Pangaea, two other scenarios have been proposed, each with its own internal logic and its own community of researchers who find it plausible. The third is called Orica. In this scenario, both the Atlantic and the Pacific close roughly simultaneously, and a new ocean opens somewhere else, the result being that the continents gather not where Pangaea was, and not over the current Pacific basin, but somewhere in between, clustered broadly around the equator. The name itself suggests the new arrangement. A world ringed by this different oceanic geometry, the continents compressed into a single equatorial mass surrounded by a new global ocean. The fourth is called Amasia. This scenario draws on a concept called orthoversion, the idea, developed by some researchers as a complement to the introversion and extroversion models, that each new supercontinent does not simply reassemble where the last one was or on the opposite side of the planet, but rather forms roughly 90 degrees away from the previous assembly, over the subduction girdle, the ring of subduction zones that surrounded the previous supercontinent and eventually drew the continents back together. In the Amasia model, the continents, all of them except Antarctica, which remains marooned at the South Pole under its ice, drift northward and gather around the Arctic. The North Pole, in this future, is a continental interior rather than an ocean. The geometry of the world is inverted from what we know. 4 possible futures, all of them genuine scientific proposals, all of them internally consistent with the physics of plate tectonics as we understand them, and none of them certain. None of them a prediction in the way a weather forecast is a prediction, because the timescales involved exceed by orders of magnitude anything that can be extrapolated from present conditions with reliable precision. They are scenarios. They are the range of outcomes that the physics permits, the envelope of possibilities within which the actual future will eventually, slowly, without any awareness of our interest in it, unfold. And yet there is one feature common to Pangaea Ultima in particular, one property of that specific scenario, that gives the climate modelers their most striking results. And that is the question of where new subduction begins. For the Atlantic to close, for the introversion model to operate, something has to change. Right now, the Atlantic is not subducting along its edges. The eastern coast of North America, the eastern coast of South America, the western coasts of Europe and Africa, these are passive margins, geologically quiet. The trailing edges of continents that have been separating since the days of Pangaea, bordered by shallow continental shelves and deep ocean floor, but no active subduction, no volcanoes, no earthquakes of the magnitude that mark the Ring of Fire. For the Atlantic to begin closing, a new subduction zone has to initiate somewhere along those passive margins. Or the existing small subduction systems that do exist in the Atlantic, the Lesser Antilles arc in the Caribbean, where the Atlantic floor is already subducting beneath the Caribbean plate and producing the volcanoes of that island chain, and the Gibraltar arc at the western entrance to the Mediterranean, another small but real subduction system. One or both of those would have to grow and propagate until they are drawing the Atlantic floor into the mantle with enough slab pull to reverse the spreading dynamic. Whether that will happen, and when, is one of the genuinely open questions in geodynamics. The Lesser Antilles subduction and the Gibraltar arc are real. They are active now. But whether they represent the embryonic beginnings of a system that will eventually pull the Atlantic shut, or whether they will remain small and locally significant without ever growing to dominate the Atlantic's fate, is not known. It is one of the key uncertainties that separates the Pangaea Ultima scenario from the Nova Pangaea scenario, and it is the kind of uncertainty that honest researchers readily acknowledge when discussing the deep future. What makes it easier to think about is to look at the world not as it is projected to be, but as it is now, and to find in the present the same forces operating at human observable scales, the same mechanisms that drove the assembly of Nuna and Rodinia and Pangaea, visible in the landscape and the seafloor of today, in places you can actually go and stand and feel the ground moving beneath you, or very nearly. In the northeastern corner of Africa, where the continent thins and fractures along a system of great elongated valleys stretching from the Afar region in Ethiopia southward through Kenya and Tanzania and Mozambique, the African plate is tearing itself apart. The East African Rift is a live example of the earliest stage of what could eventually become an ocean basin. Though eventually, here, means tens of millions of years at the very least. The rift valleys of East Africa are places where the crust is being stretched, thinned, fractured, where volcanic activity is common, and where the land surface, in some places, lies below sea level, even though it is far from the coast. The Danakil Depression, in the Afar region of Ethiopia, is one of the strangest landscapes on Earth precisely because of this, a place where you can walk on surfaces of salt and sulfur and basalt that are, geologically speaking, ocean floor before the ocean has arrived to cover them. The floor of an incipient sea that does not yet exist. Geologists sometimes speak of it as a place where you can watch a new ocean being born in slow motion. The crust pulling apart, the mantle beginning to well up, the first thin films of basalt being laid down that will someday, if the rifting continues, become the floor of a seaway that will separate East Africa from the rest of the continent, the way the Red Sea has already separated Arabia from Africa. The way the Atlantic separated South America from Africa 200 million years ago. And the Red Sea is worth thinking about for a moment, because it is another live example, slightly further along in the same process. Arabia is moving away from Africa. The Red Sea is a young ocean, narrow and elongated, geologically speaking barely begun, but real, a genuine seaway with a spreading ridge running down its centre, widening at a few centimetres per year. The same physics operating at the same pace as the mid-Atlantic ridge, but in a much smaller basin. A basin that has not yet had enough time to become truly vast. If you could watch the Earth from orbit over the next 20 million years, you would see the Red Sea widen, the Gulf of Aden deepen, the East African Rift gradually flood as the crust thins enough to drop below sea level. And the eastern fragment of Africa, the Horn, the great arc of what is now Somalia and Kenya and Tanzania, begin to drift away as a separate plate, carrying its own mountains and valleys and the last habitats of creatures not yet born. This is rifting, observable in the present, confirming the mechanism that the rock record of the deeper past already told us was real. And then there is the Mediterranean. If the East African Rift is a demonstration of a young, opening system, the Mediterranean is a demonstration of a dying one. The Mediterranean is not a young ocean. It is a remnant, a surviving fragment of the Tethys Ocean, that ancient embayment that occupied the eastern part of Panthalassa, that wedged its way between Gondwana to the south and Laurasia to the north during the long fragmentation of Pangaea. The Tethys has been largely consumed. Its floor has been subducted, returned to the mantle, gone in the way that all oceanic crust eventually goes, swallowed, recycled, leaving behind only the rocks that were scraped off the descending slab and plastered onto the overriding plate in belts of deformed and exotic material that geologists call ophiolites, slices of ancient seafloor now exposed in mountain ranges, carrying fossil organisms from an ocean that no longer exists. What remains of the Tethys is the Mediterranean, pressed between the converging masses of Africa and Europe. Africa is moving northward, Europe is more or less stationary, or moving northward more slowly. The gap between them is closing, slowly, at the rate of a centimetre or two per year, and has been closing for tens of millions of years. And the evidence of that closing is written in some of the most spectacular mountain ranges on Earth. The Alps, those great ridges of folded and thrust faulted rock that run across Switzerland and Austria and northern Italy, are the product of Africa pushing northward and the rocks of the ocean floor and the continental margins being crumpled and stacked and heaved upward between them. The closing of the Tethys built the Alps, built the Carpathians, built the mountain ranges of Turkey and Iran, built the chains that extend all the way to the collision zone of India with Asia. Because all of that, all of it, from the Alps to the Himalayas, is part of the same grand convergence, the same closing of the space that the Tethys once occupied. The same northward drift of the fragments of Gondwana into the underside of Eurasia. India is the most dramatic case. India was once part of Gondwana, attached to what is now Antarctica and Australia and Africa and South America in the great southern supercontinent that constituted the southern half of Pangaea. When Pangaea began to break apart, India began to drift north, moving over the mantle at a pace that was, for a continental plate, remarkably fast, perhaps 15 centimetres per year at its fastest, significantly quicker than the average plate velocity, pushed and pulled by the mantle beneath it and the subducting oceanic crust ahead of it. And then, roughly 50 million years ago, the ocean that had separated India from Asia was consumed. The last of the Tethys in that region descended into the mantle, and the leading edge of India met the southern edge of Asia in a collision that is still ongoing, still producing earthquakes, still pushing the Himalayas and the Tibetan Plateau upward at rates that would be measurable in a human lifetime if you had instruments sensitive enough to catch them. And we do now. And they are. The Himalayas are not finished growing. India is not finished moving. It continues to press northward at a few centimetres per year, and the collision zone continues to deform, the plateau continues to rise slightly, the earthquakes continue to mark the boundary where two great masses of buoyant continental crust are being compressed together, and neither can subduct beneath the other, because both are too light to sink. The Himalayas are, in this sense, a traffic jam of continents, and the jam is not resolved. It is ongoing. It is happening now, at this moment, while you lie still. And Australia is also moving. Australia, which separated from Antarctica roughly 80 million years ago and has been drifting northward ever since, is one of the fastest moving major plates on Earth, travelling at roughly 7 centimetres per year, faster than India now moves, faster than the Atlantic spreads. Australia is heading toward Asia. In tens of millions of years, depending on the model, Australia may collide with island arcs and continental fragments that already crowd the Western Pacific, compressing the space between it and Asia, perhaps eventually welding itself to the Asian mainland and becoming part of a larger continental mass. It is already close enough that the Wallace Line, the invisible boundary between the fauna of Asia and the fauna of Australia, the boundary that Alfred Russel Wallace noticed in the 19th century, and that reflects millions of years of biogeographic separation, has been shifting as the shallow seas between Australia and the islands of Southeast Asia gradually change character. These are not speculations. The GPE's measurements that track Australia's northward drift are as reliable as any measurement in science. 7 centimetres per year. In 250 million years, at that rate, Australia would have travelled 17,500 kilometres, roughly the distance from Sydney to London and back again. Though of course the rate will change as the dynamics around it change, as other plates adjust, as the mantle flow patterns shift in response to the ongoing subduction and spreading that modifies the whole system continuously. But the direction is clear. Australia is going north. It is one of the building blocks that will, in some combination depending on which of the 4 scenarios proves closer to correct, contribute to the assembly of whatever comes next. And yet, even with all of this, even with the GPS data and the magnetic stripes and the paleomagnetism and the zircon age peaks and the fossil distributions and the modelled mantle, flow and the satellite gravity measurements and all the extraordinary accumulation of evidence and analysis that modern geoscience has brought to bear on this question, the honest answer remains that beyond about 50 to 100 million years, the future is genuinely uncertain. The further you project plate motions forward, the wider the error bars grow, the more sensitive the trajectory becomes to small differences in initial conditions and to dynamic feedbacks that are difficult to anticipate. The 4 candidate supercontinents, Pangaea Ultima, Nova Pangaea, Aurica, Amarcia, are not 4 competing predictions of which one will be proven right by an observation. They are 4 scenarios, each internally consistent, each supported by some set of plausible assumptions about how the key uncertainties will resolve. Which of them, if any of them, resembles what the Earth will actually look like in 250 million years is something no living being will ever know, and something no instrument yet conceived could tell us. What the models can do, though, is this. They can take a given configuration, one of the 4 futures, or any other specified arrangement of continents, and they can run a climate simulation on top of it. They can ask, given this geometry of land and ocean, given this amount of solar radiation, given this concentration of CO2 in the atmosphere, what would the climate look like? What would the temperatures be in the interior, at the coasts, at the poles? How would the ocean circulation behave? What would the monsoon patterns be? And then they can ask the biological question, would conditions like these fall within the range that mammals can tolerate, or would they exceed it? And it is exactly this question, the question of whether the next supercontinent assembly, if it proceeds roughly according to the Pangaea Ultima scenario, would produce conditions that exceed what mammals can physiologically survive, that the 2023 study from Alexander Farnsworth and his colleagues at the University of Bristol set out to address in more systematic and detailed form than had been done before. The results of that study and the reasoning behind them and the 3 converging clocks that drive the outcome and the biology of why mammals in particular face a ceiling that other life forms do not. All of that belongs to the next movement of this descent, to the part of the story where the 3 ticking mechanisms are laid before you one by one. And the modelled temperatures are described not as abstractions, but as sensations, as the felt reality of a world interior so hot that the air itself becomes a hazard and the body's own heat has nowhere to go. For now, let the present-day illustrations settle. Let the East African rift be in your mind, that slow tearing in the Ethiopian highlands, that Danakil depression where the future ocean floor bakes in the sun, waiting for the water that will not arrive for millions of years. Let the Mediterranean be there too, shrinking almost imperceptibly between Africa and Europe. The last waters of a vanished ocean still lapping at the shores that will someday press together. Let the Himalayas stand as they are, still rising, still the product of a collision that has not ended, still the largest monument on Earth to the force that gathers continents together. And let Australia drift northward in the dark at 7 centimeters per year, carrying its marsupials and its ancient rocks and its record of billions of years of planetary history toward a rendezvous whose nature even the most careful models can only broadly suggest. The plate beneath you is moving. You cannot feel it, but it is moving. Every continent on Earth is in motion at this moment, shifting millimeter by millimeter, in directions determined by the ancient circulation of the mantle and the weight of old cold slabs descending into the deep. The Atlantic is widening. The Pacific is narrowing. The Mediterranean is slowly closing. The East African rift is slowly opening. All of these things are happening simultaneously, at different rates, in different directions, the whole surface of the planet in a slow, continuous, intricate waltz of stone. And somewhere in the long arc of that motion, somewhere in the 250 million years that separate this moment from the projected assembly of whatever supercontinent eventually emerges, lies the answer to the question the title of this journey posed. Not whether it will happen, because the cycle is real and the mechanism is documented and the precedents are written clearly in the rock. But what it will mean, what it will feel like, in the only sense that matters for creatures like mammals, what the air will be like, and the ground, and whether anything shaped like us, descended from anything shaped like us, will be able to draw breath in the interior of a continent that has gathered itself together around the remnant of an ocean and then begun, slowly, to bake. That is where this descent goes next. Into the heat, into the 3 clocks, and the numbers, and the physiology, and the question of whether the story of mammals, the story that began in the shadow of the dinosaurs and reached its present strange, self-aware chapter on a planet that is, by any geological standard, in a temporary and fragile configuration, has a ceiling written into the deep future of the planet itself. Not by catastrophe, not by impact or eruption alone, but by the slow, patient, indifferent mechanics of the very ground we are made of. 3 clocks. That is the way to hold it in your mind as this descent moves into the heat, into the part of the story that carries the weight the title promised when you first pressed play and found a quiet place to lie down. Not one catastrophe, not a meteor, not a single supervolcano, not a runaway warming event caused by a single driver arriving all at once and overwhelming everything in a decade or a century. 3 clocks, running independently, each set in motion by a different mechanism, each ticking on its own terms toward the same distant moment. And the thing that the 2023 study, led by Alexander Farnsworth at the University of Bristol, found, the thing that earned it a place in Nature Geoscience and set off a quiet shiver in the paleoclimate community, is that those 3 clocks are converging. They are not synchronized by design. There is no intention in their alignment. The universe is entirely indifferent to the fact that they happen to arrive together. But they do arrive together in the deep future, in the era of Pangaea Ultima, And the question the Farnsworth model asked, bluntly, rigorously, by coupling a climate simulation to the projected configuration of the assembled supercontinent, was simply this: when all three clocks strike at once, what happens to mammals? The first clock is the one you already understand from everything this journey has covered. It is the supercontinent's own interior. Continental interiors are hostile places. They have always been hostile places. The geologic record of Pangaea is full of red beds, the oxidized iron-stained sediments that form under hot, dry conditions, and evaporites, the thick crusts of salt and gypsum that crystallize when shallow inland seas evaporate in desert heat. And both of these are the signature of what climatologists call continentality, the amplified, unmoderated climate of a landmass that has pulled itself too far from the ocean to receive its moisture or its mercy. The ocean is the planet's thermostat. It absorbs heat slowly and releases it slowly, smoothing the extremes, keeping coastal climates within a range that life can navigate. But the interior of a continent the size of Pangaea, a single landmass covering roughly a third of the planet's surface, is too far from any coast for that moderation to reach. The moisture evaporates before the clouds can travel that far inland. The seasonal swings are enormous. The modelling evidence, supported by the sedimentary record, suggests that the interior of Pangaea ran mega-monsoon circulation, a vast, lurching seasonal reversal of wind and pressure that brought intense rain to the margins and left the core in brutal aridity, temperatures swinging by tens of degrees between the wet season and the long, scorching dry. And Pangaea Ultima, in the models, produces something similar. The Atlantic closes. The continents gather, and the interior of the resulting landmass, Africa and Eurasia and the Americas pressed together, the coasts receding inward on all sides, the ocean hundreds and then thousands of kilometers away from the center of the assembled whole, begins to run its own version of that engine. Hot by day, cold by night, arid through most of the year. The kind of temperature extremes that no ocean is close enough to soften. This is the first clock. It is slow, and it is structural, and it does not depend on anything happening to the sun or to the composition of the atmosphere. It is simply what happens to any interior that grows large enough. The Farnsworth model applied the physics of that interior honestly, and what the physics returned was not comfortable reading. Monthly mean temperatures across large portions of the projected land surface, reaching into ranges around 40 degrees Celsius, and in the hottest zones higher still. Up to 70 degrees in some interior scenarios. Not every year, not everywhere at once, but often enough, and extensively enough, that the question of whether a mammal could survive in the interior stops being a question about extremes and becomes a question about the average. The second clock is older than the planet's own biography as a living world. It is the sun. Stars brighten as they age. This is not a peculiarity of our particular star. It is a consequence of stellar physics, of the gradual change in the sun's core as hydrogen is consumed and the pressure dynamics shift, slowly increasing luminosity over billions of years. Our sun is currently brightening at roughly 1% per 110 million years. That number sounds small. And on a human timescale, on a civilizational timescale, on any timescale shorter than tens of millions of years, it is effectively invisible. The change in any given century is far smaller than natural climate variability. But in 250 million years, the arithmetic is straightforward. The sun will be on the order of 2.5% more luminous than it is tonight. 2.5% more energy arriving at the top of the atmosphere. 2.5% that the planet must radiate away or absorb, with consequences that cascade through the entire climate system. 2.5% sounds small, still, but the climate system is not linear. Small changes in forcing can produce large changes in outcome, particularly when feedbacks are engaged, when more heat leads to more water vapor in the atmosphere, which leads to more heat, which leads to more evaporation, which leads to more water vapor. In a ladder of amplification that has operated throughout Earth's history and that the models of the deep future must account for. The sun's brightening is a background forcing that operates underneath everything else, raising the baseline from which all the other changes, continental geometry, volcanic outgassing, atmospheric composition, are working. And it is inescapable. There is no geological mechanism that cancels it out. No amount of continental rearrangement reverses the physics of the sun's core. It is the one clock in this convergence that runs on astronomical time, not tectonic time, and it will still be running long after the last supercontinent has assembled and dispersed and the planet has become something altogether different from what it is now. The third clock is volcanic. It is the CO2. Where continents are converging, where subduction zones are active and mountain chains are rising and the crust is being reprocessed through the mantle, there is volcanic outgassing. The assembly of a supercontinent is not a quiet process. The closing of an ocean involves vast amounts of oceanic crust descending into the mantle, where it is heated and partially melted, releasing gases that have been stored in the rock since that crust formed at a mid-ocean ridge millions of years before. Carbon dioxide comes up through that process. It rises into the atmosphere along the volcanic arcs that parallel the subduction zones, and it accumulates, slowly, in concentrations that the silicate weathering cycle can eventually draw back down, but only over millions of years, and only if enough fresh rock is exposed to rainfall. The Farnsworth model considered scenarios in which the CO2 concentration in the atmosphere roughly doubles from today's levels, driven by the intensified volcanism of Pangaea Ultima's assembly zones. That is a scenario-dependent number, as any projection reaching 250 million years into the future must honestly be, and the exact value would depend on the pace of weathering and the timing of volcanic episodes that no model can specify precisely. But the direction is clear. An assembling supercontinent, with active subduction along its margins and rising mountain belts shedding material into weathering cycles that struggle to keep pace, is a plausible CO2 source on a scale that matters. And CO2 matters in this context for more than one reason. The first reason is the obvious one: greenhouse warming, the additional blanket of heat retained in the atmosphere because infrared radiation cannot escape as easily. But the second reason is subtler, and it is a thing that mammals experience directly and personally. Carbon dioxide at very high concentrations well above anything present in Earth's atmosphere today, is a cognitive impairment. It interferes with the blood's ability to regulate its own chemistry. It slows thought. At extreme levels, it is physiologically toxic. For a creature that depends on rapid, coordinated behavior to find water and avoid heat, impaired cognition is not a secondary concern. It is a survival issue in its own right, layered on top of the temperature, compounding the difficulty of existing in an atmosphere that is increasingly hostile to the biochemical machinery of warm-blooded thought. So the three clocks are the baking interior of the assembled continent, the brightening of the sun, the rising CO2 from volcanic outgassing along the assembly zones. Each one, in isolation, might be survivable. Each one, historically, has been survived. The planet has been warmer than today. The planet has had higher CO2 than today. The planet has had vast continental interiors before. But the specific combination, all three arriving simultaneously, in an era when the sun's baseline output is already elevated, reinforcing one another through the feedback loops of water vapor and atmospheric chemistry, is what the Farnsworth study argued tips the result from harsh to lethal. Not for everything, for mammals specifically. Which brings the question to physiology. Mammals are endotherms. They generate their own heat internally through metabolic processes that run continuously, and they must shed that heat to the environment or their core temperature rises to levels that disable the enzymes and proteins that run the very processes producing the heat. It is a treadmill. The metabolic engine generates warmth as a byproduct of function, and the body's cooling systems, sweating, panting, radiating heat from skin and extremities, seeking shade, seeking water, must dispose of that warmth fast enough that the core stays within a narrow window, typically somewhere in the range of 36 to 38 degrees Celsius for most mammals, above which things begin to fail in cascading ways. The limiting factor is not simply air temperature. It is wet bulb temperature, the temperature that accounts not just for how hot the air is, but for how much moisture the air already contains. Wet bulb temperature is what you get when you place a wet thermometer in the air and let it reach equilibrium. If the air is dry, evaporation cools the wet bulb below the actual air temperature. And that gap is the space in which sweating works. Evaporation from the skin surface carries heat away because the sweat turns from liquid to vapor, and that phase transition requires energy, and that energy comes from the skin, cooling it. But if the air is already saturated, if the humidity is high enough that the wet bulb temperature approaches the dry bulb temperature, then evaporation slows. The cooling effect diminishes, and at a certain point it stops working altogether. The threshold for human physiology, and for most large mammals, sits around a sustained wet bulb temperature of approximately 35 degrees Celsius. At that point, even a healthy young adult in the shade with access to water cannot shed metabolic heat faster than the body produces it. Core temperature rises, and there is no behavioral response, no degree of rest or water intake, no acclimatization developed over years of living in a hot climate that overcomes that ceiling. It is a hard physiological limit built into the way wet bulb thermodynamics interact with mammalian biochemistry. Some more recent experimental work suggests the real functional threshold for young healthy humans may be somewhat lower, perhaps around 31 degrees Celsius wet bulb, meaning the window closes earlier than the theoretical ceiling, in practice, for bodies under ordinary physiological conditions. The exact number varies by individual and by the level of metabolic activity required. But the direction is consistent, there is a ceiling, and it is not negotiable through adaptation within a lifetime or a century. It is written into the physics of water and heat. For large-bodied mammals, the ceiling is even more constraining. Body size matters because of the relationship between surface area and volume. A large animal has proportionally less surface area relative to its volume than a small animal does, meaning less skin through which to shed the heat generated by a larger metabolic engine. Large animals overheat faster in humid heat, shed heat slower per unit of metabolic rate, and have fewer behavioral options for escaping the constraint. The very success of mammals, the trend toward large body size that accompanied the Cenozoic, the era of mammals that followed the end Cretaceous extinction, would, in the interior of Pangaea Ultima, become a liability rather than an advantage. The Farnsworth model looked at this combination: the baking interior, the elevated baseline from a brighter sun, the CO2 amplification, the wet bulb ceiling, and returned a projection for what fraction of Pangaea Ultima's land surface would remain within the thermal tolerance of mammals. The numbers were not reassuring. Only around 8 to 16% of the land surface in the modelled scenarios remained in a range where mammals could plausibly survive. Not 8 to 16% of the interior, where conditions are worst. 8 to 16% of the total land area. Narrow fringes of coast where ocean moisture moderates the extremes. Higher elevations where altitude brings cooler temperatures. Polar regions, if any, remain without ice caps, and the same solar brightening and CO2 loading that make the interior uninhabitable are also suppressing the conditions for polar ice. The habitable remnant of the land would be fragments, edges, the margins of a continent so large that most of its surface has moved past what mammalian physiology can endure. And the planet has done something like this before. Not at this exact combination of clocks, not with a sun this bright and CO2 this elevated and a continent this large all at once. But the precedent exists. The end Permian extinction, approximately 252 million years ago, is the closest analogue the rock record offers, and it is, by every measure, the worst extinction event in the history of complex life. Somewhere around 90% of marine species vanished. Somewhere around 70% of terrestrial vertebrate species vanished. The deep ocean chemistry went anoxic. Reefs collapsed. The record of terrestrial ecosystems, already set on the vast, arid interior of Pangaea, shows a landscape devastated by heat, aridity, and the chemistry of a disrupted atmosphere. The driver was the Siberian Traps, a volcanic episode of enormous scale, releasing CO2 and methane and sulfur compounds into the atmosphere over perhaps 1 million years, on a continent that was already running the continentality engine at full amplitude. The Siberian Traps were not a single eruption. They were a sustained outpouring of lava and gas across an area larger than modern Europe, running long enough that the cumulative atmospheric loading crossed thresholds the biosphere could not absorb. The parallel to Pangaea Ultima is not exact. The Farnsworth scenario is not the end Permian happening again in the same way. But the logic is the same: a supercontinent, an amplified interior, elevated volcanic activity, disrupted atmospheric chemistry, and a biosphere pushed past the survival envelope of dominant groups. The end Permian was the end of a world. The survivors, the ancestors of modern reptiles, the early mammal-like therapsids, the first archosaurs, were small. They were opportunistic. They were not the dominant forms of the previous era. The Earth that came back after the end Permian took millions of years to rebuild its ecosystem complexity. And the rebuilt world was different in its architecture, different in its dominant forms, different in the opportunities it offered to the lineages that had held on through the collapse. Then the second great tectonic disruption, the Central Atlantic magmatic province, approximately 201 million years ago, erupting as Pangaea began its breakup, associated with the end Triassic extinction, smaller than the end Permian, but still a catastrophic pruning of the tree of life, the rifting of a supercontinent, the opening of the Atlantic in its infant stages. driven by the same mantle upwelling that would eventually push the continents into their current configuration, produced a volcanic province whose carbon pulse altered the atmosphere enough to cross the survival threshold for major groups. Not just assembly, then. Assembly and dispersal, the full Wilson cycle, are both extinction engines. The planet has been doing this to its passengers for a very long time. And here is the symmetry that sits quietly at the center of this whole deep time story. The end Permian extinction is approximately 252 million years in the past. Pangaea Ultima is projected to assemble approximately 250 million years in the future. The gap between those two numbers is, on geological timescales, essentially nothing. The same span of time that separates us from the worst mass extinction in the history of complex life, measured in the opposite direction, brings us to the projected date of the next supercontinent's assembly and the lethal convergence the modelling suggests will accompany it. And the age of mammals, the era that began when the dinosaurs were swept away approximately 66 million years ago, that produced the lineages of whales and elephants and bats and rodents and primates and every warm-blooded, metabolically expensive, cognitively elaborate creature that currently dominates the terrestrial biosphere, is not even 1/4 of that 250 million year interval. The mammal era, measured against the timescale of the supercontinent cycle, is a short chapter. An episode, a season in the long year of plate tectonics. And yet here it is, still running, still elaborating, still producing new forms and filling new niches and, in one very recent and very strange expression of itself, becoming self-aware enough to reconstruct this history from zircon crystals and sedimentary chemistry and the equations of fluid dynamics, and to look forward along the same arc and say, we see a ceiling. We see, in the modelled deep future, a configuration in which the ground itself becomes hostile to what we are. This is the honest point to hold. 250 million years is an incomprehensibly long time. It is not tomorrow. It is not next century. It is not within the planning horizon of any institution or civilization or biological lineage that has ever existed on this planet. The reassurance is real, and it is worth offering plainly. Whatever challenges the next 250 million years hold for the descendants of mammals, and the challenges will be many, because the climate will continue to shift, and the continents will continue to drift, and the sun will continue to brighten on a schedule entirely its own. The specific configuration described by the Farnsworth model is not a near-term threat. The Atlantic is still widening, the continents are still dispersed. The arrangement that permits mammals to live across the breadth of the planet's land surface, in temperate zones and tropical forests, and Arctic tundra and high-altitude grasslands and coastal margins of every kind, is still intact. It is temporarily intact. But it is intact tonight. And some researchers are honest enough to hold the counter-scenario alongside the projection, and they are right to do so. 250 million years is also long enough for evolution to work in ways that the modelling cannot predict. The mammals that will inhabit whatever Earth exists in 50 million years, or 100 million, or 200 million, will not be the mammals of today. They will be descendants shaped by pressures that do not yet exist, adapted to conditions that have not yet arrived, carrying solutions to problems that have not yet been posed. Evolution has surprised the planet before. The survival of mammalian lineages through the end Cretaceous, through the impact that ended the Mesozoic, that darkened the sky and collapsed the food chain and ended the reign of the non-avian dinosaurs, was not predicted by any model. The small, burrowing, generalist forms that held on through that catastrophe became the ancestors of everything warm-blooded that moves across the planet today. It is not impossible that the same principle applies to the deep future, that some lineage, adapted to coastal margins or to high-altitude refugia or to some thermal physiology we cannot currently envision, carries the mammalian experiment forward even through the baking interior of Pangaea Ultima. The Farnsworth model does not claim to know that no mammal survives. It claims that the conditions across most of the land surface will exceed the survival envelope of mammals as they currently exist. What evolution does with the remnant populations in the 8 to 16% of habitable fringe is a question the model cannot answer. But there is another piece of the long arc, and it is the quietest of the night's deep thoughts, the one that opens a perspective larger even than the supercontinent cycle. Earth's internal heat is not constant. The planet was formed hot, from the collisions and compressions of planetary formation, from the heat of the iron sinking to form the core, from the early radioactive elements that have been decaying since the solar system condensed from its parent cloud. Some of that heat is primordial, residual, still slowly leaking outward through the mantle and the crust. Some of it comes from the ongoing decay of radioactive isotopes, uranium, thorium, potassium-40 in the rock, a slow and steady internal furnace that has been running since before the first supercontinent assembled. But the fuel is finite. The radioactive elements decay toward stable daughters, and as they do, the rate of heat production inside the planet declines. Over billions of years, the internal heat output of the Earth is decreasing. The mantle is cooling. The convection that drives the plates is, on the longest timescales, winding down. This means that the supercontinent cycle itself will not run forever. The engine that powers plate tectonics, the same engine that has assembled and shattered Columbia and Rodinia and Pangaea and Pangaea, that is currently moving the Pacific plates toward their subduction zones and widening the Atlantic at the mid-Atlantic ridge, will eventually lack the vigor to sustain itself. Pangaea Ultima, if the models are correct, may be among the last few supercontinents that Earth will ever form. The assembly and dispersal that have punctuated the planet's biography at roughly 400 to 600 million year intervals may, over the next billion or 2 billion years, slow and then stop, as the mantle loses the heat that drives the convection. As the plates thicken and the rifting becomes harder to initiate and the subduction zones stall, Earth, in its very deep future, a billion years or more from now, may become a quieter planet. A planet without the great continent gathering engine. A planet where the land surface, whatever its arrangement by then, is no longer in motion in the same restless, planetary scale way. That is the longest view. And it places the supercontinent cycle in its own temporal frame, not an eternal recurrence, but a phase of Earth's biography, long and rich and consequential, but bounded. The planet had an infancy in the Hadean and Archean, when the crust was still forming and the plate tectonics were, if they operated at all, operating differently. It has its current middle age, billions of years of ocean crust subduction and continent crust assembly, and the cycles of ice and warmth and life, and it will have a long, slow conclusion in which the internal engine gradually quiets and the surface stills and the Wilson cycles cease. And whatever life remains, if anything remains, across the timescale of the Sun's own evolution toward its red giant phase billions of years hence, which is an entirely different clock and an entirely different story, will exist on a planet that no longer reshuffles its cards in the same way. Pangaea Ultima, then, is not just the next supercontinent. In the modelling, it is perhaps one of the last great gathering of the landmasses, the last time the Wilson cycle completes in full, the last expression of the engine that has been running since before anything with eyes existed to look at the sky. And the creatures that might inherit whatever follows it, if any warm-blooded, metabolizing, thinking things do find their way through the baking centuries of the assembly and into the distant dispersal that presumably follows, will stand on a planet that is, geologically speaking, beginning to rest. Outside, the ground is still tonight. You cannot feel it moving. That is the thing about this particular truth. It asks nothing of your senses, demands nothing of your attention in any moment you are awake and going about your life. The plates are shifting. The Atlantic is widening a few centimeters every year, the same pace your fingernails grow, the same quiet biological arithmetic running without your noticing. Somewhere in the eastern Pacific, cold oceanic crust is descending into the mantle along the subduction zones of the Ring of Fire, carrying the sediment of ancient seafloors back into the deep rock from which they originally came. Somewhere in East Africa, in the Afar and Danakil Depression, the crust is thinning and stretching and pulling apart at the edges of a rift that may, in tens of millions of years, become a new ocean. Somewhere in the Mediterranean, Africa is pressing northward against Europe, closing, slowly, the remnant of an ocean that existed before mammals existed, before dinosaurs existed, before most of the creatures whose fossils we now study to understand the past had yet evolved to leave a record in the rock. All of this is happening simultaneously. All of this is the same process, the same engine, the same planetary scale circulation of heat and pressure and gravity that has been running since the first crust solidified from the magma ocean and began to move. The supercontinent cycle is not a feature of Earth's history. It is Earth's history, or a very large part of it, the tectonic biography of the planet, written in zircon crystals and in magnetic stripes on the seafloor and in the folded mountain belts where continents have pressed against each other and left their record in the deformed, heated, metamorphosed stone. And you are on it, right now. Whatever surface you are lying on, whatever corner of the planet this night finds you in, you are resting on a piece of crust that has been somewhere else, that is slowly going somewhere else again, that is part of this continuous planet-scale rearrangement. The ground beneath your body is not permanent. Nothing about the configuration of land and water on this planet is permanent. On the timescale the planet itself is measuring. The map you grew up with, the map with its named continents in their familiar shapes, is a snapshot taken at an arbitrary moment in the long, ongoing drift. A frame from a very slow film. The mammals arose in one configuration of that film. They will encounter another, different configuration. In the deep future, perhaps several different configurations. As the continents continue their motion beyond whatever arrangement Pangaea Ultima represents, assuming the engine runs long enough to complete more cycles after that one. And what each configuration means for the life it carries, whether it tips toward the snowball Earth of Rodinia's breakup, toward the end Permian devastation of Pangaea's era, toward something milder, or toward the lethal convergence the Farnsworth model projected for Pangaea Ultima, depends on the era's particular combination of factors, where the sun is in its brightening, what the atmospheric CO2 is doing, how the rainfall patterns distribute moisture, where the continents sit relative to the equator and the poles. The planet does not choose. The planet does not care. The planet runs its physics and its chemistry with perfect, impersonal consistency, and the outcomes cascade from the initial conditions the way they always have. Life has been adapting to those cascading outcomes for nearly 4 billion years. Finding the margins, filling the niches, evolving solutions to problems that arrive on geological timescales. The end Permian killed 9 in 10 marine species. The survivors rebuilt the ocean. The end Cretaceous killed the non-avian dinosaurs and most of everything above a certain size on land. The survivors, the small and the generalist and the opportunist, became the ancestors of everything warm-blooded and breathing and thinking that currently populates the continents. Life is extraordinarily good at this, over the timescales the planet uses as its unit of measurement. It has been good at it for longer than animals existed. It has been good at it for longer than complex cells existed. The history of the planet is, in one reading, a history of survival against the background of continuous tectonic and astronomical change. And it is a history with an extraordinarily successful record so far. So take that with you as this night settles. The ground is a slow tide. You are a brief, warm chapter in a story that has been running for 4.5 billion years and will run in some form for billions more. The continents are in motion. The Atlantic is widening. The sun is brightening, 1% per 110 million years, patient and indifferent. Somewhere in the modelled deep future, 250 million years from tonight, a supercontinent may be assembling, and the 3 clocks may be converging, and the question of what that means for mammals may be finding its answer in the narrow coastal fringes where the ocean's mercy still reaches. And somewhere even further in the future, the engine that has been running all of this may be slowing, the mantle cooling, the Wilson cycles completing one final assembly and then quieting, and the planet settling into whatever its old age will look like. None of that is this night. All of that is the deep, deep background against which this night exists, the geological silence behind the ordinary sounds of wherever you are. The vast slowness against which you're breathing is a kind of furious speed. The rock beneath the ground, beneath the floor, beneath your body is moving, has always been moving, and you will not feel it. You will simply rest on it, as mammals have been resting on the moving ground since before there were names for any of these things. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. Whether you are on the edge of a closing ocean or a widening rift, on ancient cratons that have been part of every supercontinent, or on younger crust that formed at a mid-ocean ridge within the last 100 million years, the comments are there, and I read them. There are more stories here of the same slow and careful kind, waiting for whenever you want them. You have done enough for one night. The clocks are still ticking, all of them, the tectonic and the astronomical and the volcanic, but they are ticking slowly, and none of them asks anything of you in the next several hours. The Atlantic will still be widening when you wake. The Pacific will still be shrinking. The ground will still be in motion, patient and immense, and entirely unconcerned with the fact that you are asleep. Let the deep thoughts settle, and let yourself sink with them. Good night. Sleep well.